Okay, here is a step question on looking at gravitational potential energy. Let's make a start straight away. So it asks to write down an expression for gravitational potential energy at a distance r from point mass m. Really easy to recall, I hope. Gravitational potential. So I give that symbol v, and it's minus gm over r. Bearing in mind, potential just makes reference to the object which you're around, not potential energy, which is between two objects. We won't worry about the conservation of energy because this is going to take enough time here. The gravitational potential energy of mass near Earth's surface is often expressed as h, and I need to see if that's consistent with the expression here. So for number 2, let's jump straight into this. In effect, I need to say that GPE mg delta h. So a change in gravitational potential is equal to mg change in height. That's how we learn it near the surface of the Earth, because it's a nice linear uniform field near the surface of the Earth. Just to reference it there, we have G lines, and there are the equipotentials that are nice and even. However, with a radial field, they're all pointed to the center, and this starts to increase further the further away you get, because it's a radial field. So G here is minus gm over r squared, another recall, but hopefully you should know that. So now, let's work out, that's G, and potential, of course, we've written above. So let's start with the potential then. So potential is going to be minus gm, 1 over r. But I'm looking for the change in potential, so I'm moving from, let's go from here, a point to another point. And the difference between these two, delta r, we'll call it. So if I want to give a change in r, really what I'm looking for is r1 minus r2, which is in effect minus gm 1 over r1 minus 1 over r1 plus delta r, because r2 here equals r1 plus delta r, where delta r is very much less than r1. And I've called it r1, but we could just as easily call it r. Make life easier. Good, okay, how do we do this? Well, just multiply through. It gives us r1 plus delta r minus r1 divided by r1 plus delta r. But because this is very much smaller than that, we can pretty much ignore it, which is r squared gm, which gives us the final step of minus gm over r squared, or r1 squared if you prefer. Those cancel as well by delta r, which is in effect, this is the expression for G, which is in effect G delta r. And in order to get to my GPE, I merely multiply my delta V by the mass, giving me mg delta r, delta h, QED, one and the same. Okay, so it's a nice bit of a nice analogy between radial fields and uniform fields close to the surface of the Earth, where the distances aren't much different. But here's where we get trickier here. So a spherical star of uniform density, of mass and radius is formed by the condensation due to gravitational field. So I'm going to try another bit of paper on this one, because this is going to require some maths. So in effect, what we have here is we have my star of mass m and density, and it's formed by gas and dust coming in from a very, very far distance away and settling on the surface, and therefore building the star. And I'm looking to find that the change in gravitational potentiality of the dust that's coming down is in the form of, okay, change in gravitational potential energy. Let's just start with gravitational potential is minus gm over r. And because we're now talking about densities and so on, it's probably best to think about m as product of density. And we know that m is going to be 4 over 3 pi r cubed, and of course mass times, density times volume equals mass. So let's plug that in there. Minus g 4 over 3 pi r cubed rho over r, giving us minus 4g pi rho over 3, take the r out to be squared, r squared. Excellent. Now, what do we need to know? We need to know that so this is the potential up to the surface here. It's point A. VA. Let's call it V to point A. Now, as the dust starts arriving, it's going to increase this radius by delta R. And we are looking for, though I've written that potential there, we're looking for the gravitational potential energy, the change in gravitational potential energy, which is going to be the change in potential multiplied by this change in mass. Now the change in mass is going to be, we need a volume times the density again, but of course this is going to be the height of it, so I need to multiply the height of it, delta R, by the surface area. So delta R times by the surface area is going to give me a delta volume, and then multiply that by density is going to therefore give me the mass. So my change in gravitational potential is going to be minus 4 over 3 g pi rho r squared multiplied by this mass element, which is the surface area 4 pi squared, because we've got a sphere, 4 pi r squared, by delta R by density, by the density by delta R. And this gives us 16g pi squared rho squared over 3 r to the 4 dr. Right, we're nearly there. And so the total loss of gravitational potential energy when the radius is r, so we 0 out to r, would be the integral of this between my limits of 0 and r. Let's make sure we get those the right way around, because I'm building out and looking for the change in potential as this gas falls in. Okay, hold on, here we go then. So we have 16, I increase this by 1, 5, then divide through, so 16 over 15, because 5 by 3, g pi squared rho squared. Of course the limits, just this one cancels and it leaves me with r to the 5. R to the 5. And now, because we were looking for something up here which was in the form of m squared, the last trick will be substituting the idea that m is 4 over 3 pi r cubed rho, and we need to substitute it into m squared, so my expression is going to be something m squared. So if we divide this by m squared, squared r to the 5, and I'm looking for m squared, which is 16 over 9 pi squared r to the 6 rho squared, so that's divide by, that's an aside, 16 over 9 pi squared r to the 6 rho squared. Those disappear, those disappear, the 16s definitely disappear. The 15 and the 9, well, that goes to the top, but that can come down to 5 if that comes down to 3. Oops, sorry, all of that was talking about it, nothing being shown. And this comes down with that to leave r at the bottom. So that gives us, remember I'm dividing through by 3, so that gives us 3 at the top. over 5. I've got m squared at the bottom now. Sorry, divided through, so I've got m squared at the top, g over r. And just to be pedantic, I had the minus there and I forgot about it because I was bored. Minus there, and therefore leaves me minus, that's minus 3g m squared over 5r. The same which was asked right here. Okay, it's change of gravity. What's happening? How is it conserved? So what happens is the GPE turns to kinetic energy, and then that turns to collisions as this all starts collapsing, because they collide. That turns to translational, and we know that translational kinetic energy is therefore heat, temperature, and that will be re-radiated by the star. Okay, it's quite insightful, that one. I quite like that problem. Return this over, because we're going to have another part here. And then says, determine the gravitational field strength at distance r less than the surface of the object, or from the centre of the star, and hence find the gravitational potential at the star's centre relative to a long distance away. Okay, g first. It's telling us g, so let's get g down. Minus g m over r squared. And then you're looking at something inside the star. So there is my star. Let's just draw G here. And there's the distance away from the centre. So I've got my surface going on here. And what's happening inside here? Well, m, of course, is 4 over 3 pi r cubed rho. And if I plug that into there, that gives me minus g 4 over 3 pi r cubed rho over r squared, giving me a function of minus 4g pi rho r over 3. Good. Now, so really it looks something like this, if I was to draw that in. So my function here is going to increase the proportion of minus r. I mean, I know I've drawn it the other way around, but that's a straight line negative gradient if it were going. But I've drawn that the other way around, nonetheless. But it's looking for the, it's asking me for the, and hence the gravitational potential of the star at the surface. So we know that G is the differential form of dV by dr. So V is going to be the integral of minus g dr and working that between r to 0. Because I'm going to go from the distance out back down to 0. I'm looking for the potential at the centre. This gives me the integral of 4g pi rho squared over 3 r to 0, giving me, well, of course, we're integrating this, so that becomes r squared over 2. So that's, hold on, my brain's just melted there. R squared, yes, so that becomes r squared over 2. So we've got 4 over 2 g pi rho r squared over 3. And the 4 over 3 pi, so now we substitute back in m is going to be 4 over 3 pi rho r cubed. So if I divided that, would give me a half gm rho r squared 4 over 3 divided by 4 over 3 pi. Sorry, I've forgotten the pi up there. Too many numbers going through, letters going through here. R cubed. So that means what I'm left with so far is going to be, so there's going to be an m factor at the bottom. So 4 over 3 goes to 4 over 3. Pi goes with pi. Rho goes with rho. R squared goes with r cubed. So I'm left with a half gm. I've got the m up there because that's what I've substituted. So, and that's because of my limit, that goes a minus in there because I went from 0 first, which is 0, then minus the r, giving me r. So minus in there, giving me minus gm over 2r. Okay, you might say that is the area under the graph because I've integrated this function. And then, of course, beyond there, I know this function is dropping off as 1 over r squared, function of g, and because it's at the centre from a very long distance away, because it says here, hence find the gravitational potential star at the centre relative to 0 at a very large distance from the star. In effect, I want to integrate all of this up as well to get my next expression for the area under here. However, that, if I integrate up g with respect to r from r to 0, in effect, that gives me the potential. Good. So therefore, which is, we all know, minus gm over r. So really, the addition of those two will give me the potential, which is going to be minus 3 over 2 gm over r. That is our final answer to that. Okay, hope that makes sense.